these are, as I was just saying, charts, right? That the equation is there, but for different values of n, and different values of sigma naught upon E, you have plotted these charts for plane stress or plane strain. So if we are in the field, if we are in a hurry, rather than using the whole equation, calculating this, that, we just directly see what was the n value, what was the sigma naught and E values for our given material, and then we find a value of dn. And once dn is there, then there is a relationship between J and CTOD. Now, why are these relationships critically important? That experimentally, if you can measure CTOD correctly, then you can find J. Experimentally, if you can measure J correctly, then you can find CTOD, right? And this is now in the elastic plastic region, right? Not linear elastic. You can find delta CTOD and J integral for linear elastic also, but for elastic plastic, where there is significant plasticity at the crack tip. So for that, now you have a very good relationship between the two defining quantities J and CTOD. With this relationship thing, right, now crack growth resistance curves. So again, right, that if you want to talk about crack growth, then it is the energy release rate, which is now non-linear, right? Earlier it was linear. And when energy release rate is there, then the opposite of it is the crack growth resistance curve, right? There was capital G and there was capital R resistance curve, right? So now we are talking of the resistance of the material. Many materials which have high toughness, right, like standard metals, they have a rising R curve. We explained it earlier, that rising R curve, because at the crack tip there is plasticity, there is ductility. So the resistance of the curve, the resistance of the material to crack growth becomes more because of the plasticity. So rising R curve, J and CTOD increase with the crack growth, right? So this is brilliant for us. This is brilliant for us, right? You see, this is natural. This is how materials behave. But when the materials have significant plasticity, crack growth will be fast when the material is more brittle. But when there is more and more plasticity, then the resistance of the material to crack growth will keep on increasing, right? So J and CTOD will increase with crack growth. In metals, standard metals, rising R curve is normally associated with growth and coalescence of micro voids. We will talk of it later on also, but we have talked of it in the beginning, right? That there are micro voids, very small voids, or very small fractures, or very small flaws. So growth and coalescence. One small crack is here, one small crack is here. This is also growing, this is also growing. After they grow for some time, they coalesce and become a larger crack. So the figure on the next page is a schematic illustration of a typical J resistance curve for a ductile material. There would be G resistance curve when LEFM is there. There will be J resistance curve when EPFM material is there. We will see on that graph that the initial stages of deformation, R curve is nearly vertical. A small amount of apparent crack growth due to blunting in the beginning, in the blending. As J increases, the material at the crack tip fails locally and the crack advances further. As the R curve is now rising, the initial crack growth is usually stable, but instability can be encountered later, as we will discuss shortly. So let us go to the curve. So this is now the curve. This is the J resistance curve, not J resistance curve, and this is the crack extension. Now this is brilliant. You see, I am sometimes really wonderstruck. I mean, this is a totally unrelated thing, but I am teaching different courses. I am teaching advanced applied math. I am teaching material science. I am teaching fracture mechanics now. You see, if you look at the stress-strain curve, then you get a curve which is very similar, right? A curve which is very similar. We have discussed other curves which are very similar, and now J resistance against crack extension, but the behavior is straight line region and then a non-straight line region, right? So this is unbelievable that some huge scientist has created the whole universe. We are studying hundreds of different types of metals, materials, and so on, thousands of different types. And when we study stress strain curves, all of these materials have a similar curve. We are studying now J resistance against crack extension curve for all different metals of significant plasticity or ductility. Again, the curve is very similar. So you see, if the whole universe has happened by chance, then this is unbelievable. I mean, the chance would be 1 by billions and billions, right? That it has happened by chance. Otherwise, if, as I don't remember Aristotle or Plato who said that if there is a design, then there must be a designer. If there is a design, then there must be a designer. So if all of these hundreds and thousands of different materials show a similar curve, then there must be a design in the way the materials were designed. Okay. So now the J resistance curve against the crack extension. Initially a straight line region. So this, they said, is the crack blunting region, And then as J increases a little more, there is a critical value. There is a critical value, Ji critical, J1 critical, right? The fracture toughness of the material. So crack initiation starts, and then J rises further, right? So there is this larger crack and then a small crack initiation, and then a coalescence, right? This small crack grows, this larger crack, and they join together, and then they join, and then they join. So this crack now is extending. And because it is a non-linear place, so at any point, from this point to this point, you find the change in J and the change in A. So this is the slope, dJ, dA for the JR, right? The crack resistance curve. So initially, this slope is very steep, and then this slope starts to decrease down, and so on. And the crack, you need to change J only a little for crack to grow. But here you need a big change in J for a small change in A. So the crack initiation region, you need a large amount of change in J for the crack to grow a little. But once the critical region, the J1C, the critical is gone, then only a little change in J will cause a large change in A, right? So this is the curve that we were talking about in the previous page. One measure of fracture toughness is, of course, J1C. J1 is the J integral in mode 1 loading, and its critical value is a measure of fracture toughness, right? So this is defined near the initiation of the stable crack growth. The precise point at which crack growth begins is usually ill-defined, because this is the end of the straight line region and the beginning of the non-straight line region. So sometimes it is not a precise, so it is ill-defined. So therefore, the definition of J1C is somewhat arbitrary, and it is very much like the 0.2% offset yield strength. Remember, in the stress strain curve, if the yield point is not 100% clear, then on the strain line we say 0.2% strain, draw a straight line, and then see where it goes. So similarly, if the J1C is not very clear, then we will do something like that when it is ill-defined. The corresponding CTOD, this was J1C, CTOD critical, near the initiation of a stable crack growth is denoted by delta I by US and British testing standards, right? That the initial value of delta, they could have said delta 1C, just like J1C, but because in the US standards and British standards of testing for CTOD and J, they call it delta I. So the value of CTOD that corresponds to this value of J1C is denoted as delta I in the standard methods. Chapter 7, which we are not covering, I am again referring, describes the experimental measurements of J1C and delta I in more detail. We have told you in the previous slides and so on how you experimentally measure CTOD or delta and how you experimentally measure J, the J integral. But once you want to find the plane strain fracture toughness, right, the fracture toughness value, then it is J1C, the critical value, and it is delta I, the critical value of delta. So that means again you do the standard fracture toughness test by measuring either delta or by measuring J1 and going to the critical value, right. So that experimental one for fracture toughness measurement, not general J1. J1 is the J integral at any load, but when the load becomes the critical load or the A becomes the critical A, then J1 will call J1C. Similarly, delta CTOD is at any load or any crack size, but when it reaches the unstable region, then it becomes the critical value. So those experimental procedures of finding fracture toughness under J integral and CTOD methods are described in chapter 7. We are not going into the details of that because we have described the general method, experimental method of finding J1 and CTOD or delta. Initiation toughness, right? Initiation toughness, right, at the J1C initiation point provides some information about fracture behavior of a ductile material. The entire R curve gives a more complete description, right? Initiation toughness is J1C, but the entire curve. Now slope of the R curve at a given amount of crack extension indicates relative stability of the crack growth. If you go back to the figure, right, the slope, right, dj upon dA. Material with a steep R curve, steep, not flat, right? This is less steep, this is very steep. So material with a steep R curve is less likely to experience unstable crack propagation. In the J resistance curve, slope is usually quantified by a dimensionless tearing modulus. Rather than directly saying dJ dA, they define a new modulus called the tearing modulus, TR. It is E upon sigma naught square dJ dA, right? So this is the simple dJ dA, JR resistance curve dJ dA, but you multiply it by E and sigma naught square, right? So then this slope is converted into a standard slope which is called the tearing modulus. So they define this because by this E upon sigma naught square, it will become easier to calculate things and so on. They will show later on, where this subscript R indicates the value of J on the resistance curve, right? Tearing modulus. So again, resistance, right? If it was the J curve, it will be only T. It was the JR curve, so it is TR, right? So this is there, and we will see later on. Again, as I am telling you again and again, we are not going through the mathematical derivation, but just trying to explain to us the physics or the mechanics of the problem. So with this background, we will now go to, right, we just talked of the resistance curve in terms of J integral, and now the stable and the unstable crack growth, stable and the unstable crack growth.